All right, we are recording. So, welcome to my presentation. Um, for my project, I will be comparing the recursive mathematical systems through computational generation. Um, basically, just scientific jargon for comparing fractal generation. I'll be comparing the fractal generation of three different fractals that I will go through in this presentation. My name is Ari Legal, and this is for scientific programming in Python. So, so my main point of research was how do different recursive and iterative mathematical rules generate distinct fractal geometries and behaviors. Um, Primarily, I wanted to find out how essentially different mathematical functions can produce distinct fractals. So for the three fractals that I was doing research for this project, those will be the Sierpinski triangle, Mandelbrot set, as well as the Barnsley fern. Um, all three of these fractals are generated via rather simplistic rules and mathematical functions in comparison with the shapes and the complex structures that are generated and because of these simple mathematical rules or functions. So this was my main point of research. I just wanted to know how each of these fractals kind of generates and from which these structures are building upon these very simple rules. So this is the experiment. And some of the key questions that are very important to consider while doing this project were, what is recursion? Recursion is a very important topic throughout this project because recursion is essentially how fractals are generated. You're repeating a function of some sort that's creating a pattern that creates a very complex mathematical structure that people typically wouldn't know would be produced via a very simple function. So recursion is the process of self-referential behavior through functions or coding. It is an underlying basis of why fractals exist. Good examples are factorials or the Fibonacci sequence. So factorials, some of you may be familiar with those. Those are, it's 5 and it looks like what could be an exclamation mark afterwards. It just means that you're going to be multiplying 5 by its successive integers before it. So, for example, 5 factorial will be 5 times 4 times 3 times 2 times 1. 3 factorial will just be 3 times 2 times 1. And 4 factorial, 4 times 3 times 2 times 1, so on and so forth. So those are factorials. And then there's also the Fibonacci sequence. So that few of my colleagues might also be familiar with, as that would just be the addition of the prior two numbers starting with 0 and 1. So 0, 1, 1 plus 0 begets 1, 1 plus 1 begets 2, 1 plus 2 begets 3, and then 2 plus 3 begets 5, and 3 plus 5 begets 8, so on and so forth. Division of those numbers by the previous number gets you closer to the golden ratio, a transcendental number that's denoted 1.618 approximately, but not too much on that. Why fractals matter in mathematics and computer science. Fractals help model complex structures and behaviors in a pattern-based way. So they're used a lot in computer graphics. Chaos theory is a mathematical field, and data compression. So very useful in various fields within mathematics and computer science. Why do fractals appear in nature? So as stated before, they represent complex patterns that emerge from relatively simple rules and processes. Natural phenomena also, follow these rules and often involve recursive processes. They model phenomena such as coastlines, weather patterns, and fluid dynamics, amongst others. If you think about coastlines, kind of the patterns of how waves move. Fractals can kind of model that at times. There's various other natural phenomena that do happen. Fractals can also represent weather patterns and, as stated here, fluid dynamics. So this project is mainly investigating how the different recursive and probabilistic mathematical rules generate self-similar fractal structures. So how each of these mathematical functions and rules would help generate these complex structures. So the first fractal I want to talk about is the Barnsley fern. So this is one of the iterated function systems. So this is generated using the iterated function system. It's composed of multiple affine transformations. So affine transformations, they modify the coordinate position through scaling, rotation, and translation and reflection. So if you see each of these leaves here, we kind of start at a single point. And I will explain how each of these fractals is kind of generated, but it starts from a single point, and through scaling, rotation, and translation, you produce other points that essentially start producing a stem and then produce the successive leaves that are kind of each legs on the stem, producing their own leaves, and then through the same process of rotation and translation, more stems and more leaves are kind of built off of that stem indefinitely, and you continue this process indefinitely. So for this one, this is the picture that was generated through my code. I generated over 100,000 coordinate points. There are a lot of coordinate points on this one. This is a very detailed picture. You can kind of zoom in a little bit more. This is not the best resolution. Apologize for that, but you could kind of see here. These are, they continue on forever, infinitesimally. This one is 100,000 points, but we can have pictures with resolutions that are very more exact, that are much more exact. Oh, that was not meant to do that. Apology, but that did wrap up basically what the Barnsley fern was about. Next is the Mandelbrot set. This is a relatively popular. This is a very popular fractal, one that a few people might know about. However, it's generated using recursive complex number iteration, specifically the complex quadratic formula, which again we will go over a little later in this presentation. But just to go over the general generation process, it's generated using complex number iteration. Each point in the complex plane is kind of tested for whether the sequence remains bounded or diverges towards infinitesimal zooms of the same repeated structure. So essentially, you will put, we will go over this a little later, but you will put in the function. You start at a point. Z null, and you do z squared plus c, which is a constant, and you test to see if that point is within this boundary for the Mandelbrot set. If it's not in the boundary, it'll be on the black and the exterior, and it won't be included within the fractal. However, if it is within the boundary, it will be produced on a point where the fractal will continue to self-repeat, and it does that forever and ever. So this is the example here. Visual is produced using a same-time algorithm relying on iterations. So as stated, iterations based off of this quadratic function, complex quadratic function. So for this one, I generated 1,000 by 1,000 computational grid, as shown here on the right-hand side. You can see that there. I also stored iteration depth values for each pixel and used color mapping to kind of visualize divergence behavior, as you can see here. The more intense kind of white colors showing where the fractal is, the heat, it's kind of like a heat map for the fractal. Outside of that it's darker, and then on the kind of borders you see like the red points that are kind of around the area, surrounding area. So And this produced high computational workload due to the nested iterative loops. Not too bad. We will see some of the metadata storage a little later. The final fractal is going to be Sierpinski triangle, generation by Chaos Game. So it's generated through a recursive midpoint process known as the Chaos Game. The three vertices are established as fixed points. So as you can see here, there's going to be three vertices. These are kind of the midpoints or the endpoints for each of these other triangles here, and they produce their own triangle, upside down triangle. What you essentially do is you do that same process for each triangle within. There's going to be upside down triangle and three other triangles that are produced around the upside down triangle. And you repeat the same process. Find the endpoints and you continue to do that. Kind of the midpoints of each of the ends of the triangle, and then you continue to do that. There's multiple ways to actually produce this fractal. You could do it by, as I stated, finding the midpoint of each of the edges of the triangle. You could also start by drawing one triangle and kind of producing it from the bottom up. There are multiple ways to produce this fractal in particular. So the three vertices are established as fixed points. During each iteration, a random vertex is selected and current point moves halfway towards that vertex. So this is another example. This is one of the ways. So you just repeat the process thousands of times and infinitely, and you will produce this fractal. So just simple midpoint rules recursively, and this is how this fractal is produced. So here are some of the comparisons for each of the fractals. So we have here, the first is the Barnsley-Fern. The method used was, as stated before, affine transformations, just that rotation, the translation, and the production of each of the leaves for the Barnsley-Fern. Is it random? It is relatively random due to the amount of different operations being done on certain points. So the amount of rotation and translation, you could kind of produce that fractal regardless of which point you choose. You could produce that. These are relatively random. It's recursive, as all of these are also recursive. The data generated for this fractal was coordinates, and the metadata storage was actually 1.19 megabytes. Next, the Sierpinski triangle. The method used was, as stated before, midpoint recursion. It's semi-random. You could generate this in various different ways. However, it's not as random due to less functions. As with the Barnsley fern, there's more involved in the production of that fern. Is it recursive? Yes, I stated before. The data generated for this was also coordinates, and this took up 304 kilobytes. The final one is the Mandelbrot set. This is through complex iteration, and this method is not random. This is a bounded fractal, and you are looking for points within the boundary. This is not a random process. You could start from a random point. However, this is a certain boundary. The other two fractals don't necessarily have bounds similar to the Mandelbrot set. This is also operating within the complex plane, so it's not operating the same way as the other two fractals necessarily. However, this is not random. This is recursive, however. The data generated for this was the escape time matrix. You saw that earlier. It's kind of the coordinate, but it was the that was the data generated. And then for this is the metadata storage, is 466 kilobytes for this one. So some of the issues encountered throughout this presentation included debugging of the matplotlib to render image and figure display behavior. So as the images I showed you there were some issues kind of rendering them, making sure they rendered at a proper resolution. Just resolving some runtime and variable scope errors, as well as managing the image resolution as stated and rendering quality for high point fractals such as the Mandelbrot set. Structuring the multiple fractal generators within reusable Python functions was a bit of a challenge. You will see the code. I will, when I send that in, you'll see kind of how each of the functions was kind of organized. But the outcome was that I did get an improved understanding of the recursive computation. The scientific visualization. So at full capacity, you were able to see the fractals as I showed you here. And I just understand that kind of the performance trade-offs within the computational maps for how much kind of storage you have to take up to produce higher resolution computers, or if you're going to trade off in order to produce things maybe at a lower resolution. So here are some visual code snippets. So in the middle, this is the Sierpinski triangle base code. You're kind of seeing you're starting at the vertices. You're choosing the vertices for the triangle. And then you got to produce like an X and a Y list to kind of find the vertices. Look for the middle. And then you kind of continue to produce it. And then after that, this saves the figure. And it produces the images that you had saw earlier on the slide. So that's just the first one. So this is the middle. As I stated, it works by starting from a single triangle, finding the middle point of its three sides, form an upside down triangle, apply the process to all of the remaining smaller triangles, and you repeat indefinitely. Bottom right, Mandelbrot set. So it works by complex quadratic function for all points C in the complex plane. So it starts with Z, which is Z null. Then you apply the function Z squared plus C, which is that point within the complex plane. And you determine whether this point, this function will produce a point within the Mandelbrot set or outside of it. And that's just how the fractal is generated. And you repeat that indefinitely. And as I said, this is not necessarily as random, although it does produce a very beautiful and complex structure. Bottom left corner, so you have the Barnsley-Fern. Here's the code for the Mandelbrot set, by the way. So, just kind of testing within the range, kind of test, and then you determine whether it's in the set, and you return the set, and you continue production from there. And finally, the Barnsley-Fern function snippet shows the basis of the code. You work from scaling from one point, vertically rotating, and then place points along the stem, and then you repeat. So here, kind of choosing points, rotating, and continuing. And here's the conclusion. So in conclusion, the project demonstrates that complex recursive geometric functions can emerge from seemingly simple recursive functions in systems. So despite using different recursive mechanisms, the Barnsley, Mandelbrot, and the Sierpinski triangle, they each generate large and self-similar structures for computational analysis and image generation, as you saw. And it shows that through methods involving self-referential function and code that corresponds to those correspond to complex structures emerging. And that will be it for my presentation. Thank you for listening in, and that concludes. Thank you.